Hello to all the viewers who have tuned in from different parts of the world for this virtual edition of the 2020 Bifacial PV workshop. Thanks to the organizers for giving me the chance to share with you the information on DuPont's transparent backsheet for bifacial PV applications. My name is Kaushik Roy Chaudhary. I'm the Global Technical Leader for Photovoltaic Reliability in DuPont. First up, I would like to give you a brief introduction about DuPont's products in the PV industry. DuPont has been a frontline material supplier in the industry for well over 40 years. I'm showing here three of our flagship products. Our silver metallization paste enabling higher efficiency at the cell level under the Solomet brand, the polymer-based backsheets under the Tedlar brand, the topic of our discussion today, and silicone encapsulants and sealants under the Fortison brand. All of these materials have actually enabled high performance over 30 plus years in the field in continuous deployment, helping asset owners drive down LCOE and maximize their returns. Now, talking of LCOE, I'm pretty sure all of us are familiar with the elements that contribute towards LCOE calculations. We have the costs on one hand, and module and system efficiency, durability, and energy yield on the other. I would like to recast the discussion today in a very similar but slightly different light. I would like us to look at it in terms of lowering the total cost of ownership of PV systems. In this discussion, I will be picking up topics under three broad buckets: long-term material reliability, differentiated energy yield, and lowering of some of the costs. So let's dig in. Like always, we start off with long-term reliability, especially in the field. Most of us are aware, as was pointed out probably in some of the talks earlier, module level failures are actually on the rise in the field in recent times. DuPont runs a pretty big field program globally to assess material defects in fielded modules. And what we see from our work for nearly a decade now is that recently, over the last few years, we are increasingly witnessing more module failures and more backsheet failures for that matter in the field. That's why when we launch any new product, we try to look at the field to see if we have any existing information that can inform our work and our decisions. The approach was no different when we launched our transparent Tedlar backsheet for bifacial modules. Unfortunately, bifacial photovoltaics has been only deployed in large numbers in recent years, and there are not that many older installations in the field. However, we did find some examples of an earlier generation of transparent Tedlar backsheet, which was already being sold 20 years back in building integrated PV applications. I'm showing here one such example. This was in the Netherlands. At the time of inspection, this installation was 18 years in the field. This is, by the way, now 20 years. What was important for us was the fact that there was no obvious defect, no yellowing, no delamination, no cracking, even after 18 years of continuous operation in this. This provided us the confidence, to launch the new and improved Clear Tedlar Film for the bifacial application, because the fundamental polymer chemistry in the new product is very similar to this older generation product, only with enhanced and improved packages. And in this next chart, I'm showing this Clear Tedlar PVF film, this new improved product, which was launched in 2019, and it won the PV Magazine Award then. On the right, I'm showing a cross-section of a typical backsheet structure, a tri-layer backsheet structure, and this Clear Tedlar film goes on the air side outer layer, and it protects the core layer, which provides most of the mechanical properties. Okay, when we think of the properties of a backsheet in a bifacial application, The properties that it needs to fulfill, in my opinion, are three main ones. High transparency that needs to hold up for the lifetime of the module, because you want the light to come in unhindered over the lifetime of the module. Robust mechanical properties and adequate UV protection for the inner layers of the backsheet and other polymer packaging materials, and in some cases even to protect the passivation of the cells. So here we are showing some of the initial properties of the transparent clear Tedlar film. The optical transmission of the film is about 94%, as you see here, and is rather flat across the entire solar spectrum. This is important so that the maximum amount of light is available for the rear side of the module to convert to electricity. The elongation and break numbers refers to mechanical properties, which I will come to in a moment. Okay. So next on this chart, I'm showing how these properties, the optical and the mechanical properties, hold up under relevant UV exposures. In this case, the UV exposure was through a xenon lamp, and it was at an elevated temperature. As we all know, UV light can degrade polymeric materials, so ensuring these properties are unaffected over doses that represent 25 to 30 years field operation is very important. What we see here is that there's no significant loss in UV absorbance, as we see here on the top left, after 350 kilowatt hours of UV dosage at elevated temperature, with no appreciable color change, which is typically measured in terms of the yellowness increase in these transparent films. This is shown on the top right. On the bottom left is shown the mechanical properties, the elongation of the film in both directions of the module. And this property also does not change appreciably at all, even after 350 kilowatt hours of UV exposure, which, by the way, equates to about 28 to 30 years for a nominal 15% albedo. Light transmittance, shown here on the bottom right, also stays rather flat across the entire exposure range. The next slide shows some field data from the earlier generation of the film. This experiment was conducted in Switzerland, and the results showed that light transmittance for the Tedlar film didn't really change after 20 years in the field. This was a study that was not conducted by us. In this study, the researchers also compared a PET-based transparent film, which actually became brittle and lost all transmission after 10 years of outdoor exposure. Next, we move on to properties of the transparent backsheet, which incorporates the clear Tedlar film, for which I just showed some of the properties. We first look at the optical properties. As we see here, rather flat optical transmission and very little color change, as is shown by the plot on the left, after 400 kilowatts hours of UV exposure in this case. In comparison, on the right, some other clear backsheets shown here have significant increase of color in a metal halide UV exposure, while the Tedlar backsheet maintains the low color change. Next up are the mechanical properties under UV exposure at elevated temperatures and in 3000 hours of damp heat exposures. Again, as we see here, under both these stresses, the backsheet retains its mechanical properties even at the end of these tests in both directions and stays well above 100%. Showing some more results on extended single stresses in this next slide. We have damp heat 3000, 600 thermal cycles, pressure cooker testing for 60 hours, and 360 kilowatt hours of UV exposures. For all these stresses, we see that the backsheet retains its mechanical properties, both the tensile strength and the elongation in both directions. And it also stays well above the internal benchmarks, which are represented with these red dotted lines. Once we're satisfied with the film and the backsheet level results, we now take the testing up to the next level, which is the module level. As a group, we strongly believe, like a lot of others working in this field, that in order to simulate real-world conditions, you really need cyclic and sequential multiple stresses on the same module. We have been working to develop such relevant stresses and protocols. One such sequential test that we are all familiar with is PVEL's backsheet durability sequence, which is shown here, which combines cycles of damp heat and cycles of UV and thermal cycling and humidity freeze. The transparent Tedlar backsheet in mini modules was tested in this sequence by PVEL. And as is noted here on this slide, it didn't really have any cracking, yellowing, or delamination after the test was completed, defects which are typical for backsheets in the field. Just for reference, I'm showing here how this test is effective in catching backsheet defects. I'm showing here in this case a cracking defect in a material that has also shown the same defect in the field in 4 to 5 years. So this gives us confidence that the material, the backsheet enabled by the transparent Tedlar, should have reliable, durable performance in the field for the lifetime of a module. Okay. Another question that we often get is around abrasion resistance in harsh, typically desert-like conditions. Although in my opinion, we really don't have a good accelerated test that simulates such a condition for a backsheet's lifetime in the field. However, there are some rather aggressive falling sand standard tests. We performed one such test as is shown here. It's an ASTM test, and we tracked the light transmission loss through the process and at the end of the test. What is shown here is that at the end of the test, the Tedlar backsheet shows little change in light transmission, in fact less than 1% after this harsh sand abrasion test. In comparison, a couple of the competitive products which we also had in this test lost nearly 4 to 5 times that number. Another important issue for bifacial P-PARC modules is potential induced degradation. I'm sure you must have again heard about this in other talks in this conference. There are differences between the front and the backside losses in P-PARC modules. So we wanted to test modules with a transparent backsheet and identical modules with a glass backplane. And the results are shown here on the left over here in the bar chart, where we are plotting the power loss on the back side of a module. The blue bars are glass backsheet module, and the orange bars are from glass modules. And what we see here is a clear differentiation. The power loss is clearly less in the clear backsheet module versus the glass modules. Just for reference, we actually tested these modules out to 384 hours in PID testing, which is double the time required in standards. Additionally, these commercial modules were also tested independently by a Tier 1 module maker at PVEL, and the results are shown here on the right. And the module with transparent backsheets hardly lost any power after the 192 hours of testing and retained a rather high insulation resistance at the end of the test. By the way, I also forgot to mention that for our internal test, these commercial 60-cell bifacial modules had identical POE, polyolefin-based encapsulants in their construction. Okay, now since we have looked at all the reliability aspects of the module in the film, backsheet, and the module format, let's look at the second bucket that I had talked about. Let's look at the energy generation differentiation that the transparent backsheets can bring about. I'm showing here field results of 4 different installations with data up to 8 months comparing glass and transparent backsheet modules. This was conducted by a Tier 1 module maker. And interestingly, in all cases over these multiple months, they saw higher energy generation in the transparent Tedlar backsheet modules compared to the glass. We believe that this difference came from the 1 to 2 degrees Celsius lower operating temperature of these modules compared to the glass modules. This is, we believe, again, a result of the better thermal dissipation characteristics of the transparent backsheet and the differences in the thermal transmission windows of the two materials. This difference actually can be significant for any asset owner. Okay, finally, for the next few slides, we now want to change our attention to the potential to lower operational and balance of system costs that the transparent backsheet can bring about. The first point is around potentially easier cleaning afforded by the fluorinated transparent backsheet, which can lower the operations and maintenance cost involved around cleaning. Now, the natural surface property of the fluorinated backsheet makes it repel dust, and this is seen in this field study where transparent Tedlar bifacial backed modules accumulated less dust compared to glass bifacial modules which were installed in the same area. In addition, the hydrophobic nature of the surface of the backsheet helps in cleaning the backsheet with natural cleaning agents like water from rain. This property was tested in the lab at Fraunhofer in Germany. The plot on this slide on the left bottom shows, in fact, the better cleaning efficiency that was measured by Fraunhofer of the Tedlar backsheet compared to solar glass in mini modules. This next chart emphasizes the same soiling resistance properties of the transparent backsheet as compared to solar glass, again in a standard test, where the picture clearly shows the difference after the rinsing step. The pictures on the bottom comparing the transparent Tedlar backsheet with PV glass. And now finally, I want to draw your attention to something that you probably have heard multiple times in this conference now. The transparent backsheet does offer a distinct advantage in weight compared to an equivalent glass module, being anywhere from 4 to 10 kilograms lighter in weight. As the cell sizes keep increasing and the industry keeps moving towards larger and larger panels, this difference will only widen. And this is again a clear difference that the asset owners can get through their choice. So when we put all of that together, from the aspects of sufficient and enhanced material reliability in the field to differentiated energy output, to the potential for lowering installation and operation costs, we are convinced that this solution can indeed lower the total cost of ownership for asset owners. With that, I thank you for your attention, and if you have any further questions, you can always reach out to me. Thanks again.